So, yeah, this talk basically deals with, as the title says, collecting malware, building up huge piles of malware, and then doing something useful with these huge piles of malware. So, brief introduction of myself. I'm Georg Wisiewski. I'm a developer at the mwcollect.org community. I'm a member of the Giraffe HoneyNet project, which is a subdivision of the global HoneyNet project dealing with the low interaction honeypot type of stuff. I'm an employee of MZSoft. This is a small Austrian antivirus company, and I am a student of the RWTH Aachen in Germany. So let's first talk about why we are going to do this and what is our interest in collecting malware. The basic idea is we want to monitor the bad guys and fight them, and especially bad guys here is botnets and botnet herders. And we do this by collecting and acquiring the malware through different means like low interaction honeypots like Nepenthes or Honeytrap, client-side honeypots like pHoneyC, which I'm going to introduce for the first time to the public today, and simple spam traps collecting email attachments like SpamSync. We then have all this malware, and this doesn't help us much alone, so we need to automatically analyze this malware. We're using some standard sandboxes like the Anubis sandbox, but you could also use the CW sandbox or the Norman sandbox. We have experimented with Halvar's VX class. He's going to present on it, I guess, later today. And we also developed some custom hash functions for grouping different malware binaries into specimen groups called pEhash. After analyzing these binaries and having some information what these binaries actually do, we're monitoring the botnets these malware connects to using some monitoring software, and we inform abuse departments and the like. And after doing all that monitoring stuff, we correlate all data like link botnets to binaries and botnets to attacks and all the like, and want to display it in a usable way. So because visualization is also very important, especially for the technically not so skilled. Having all these ideas, what we want to do, this is a picture of an actual setup in the MWCollect Alliance. So we actually have the malware collection stuff here, putting it all into a database where it's get fetched by the sandbox and some antivirus for having some nice signature names for these binaries. Which is again put into the database. From there, the botnet monitoring software gets the data from the database, again puts it into this, and then we have the web interface for displaying all this. So there's one central database and all these tools fetching data from it. So the first step is the malware collection, and there's several tools to do this, and I'm going to briefly outline how they work. First of all, there's Nepenthes, a low interaction honeypot, which works by emulating the known vulnerabilities. So for example, we have the LDAS exploit, there's some public exploits for it, and we just look at the source of these exploits or the information about the vulnerabilities and write some module to emulate these vulnerabilities. Then we of course are going to get some exploit from the malware with a payload like a shellcode. So we analyze the shellcode, and then just download the malware from the infecting host via HTTP, TFTP, whatever the malware uses to propagate. And then we just store it on the hard disk or submit it into the database or whatever. And since this is implemented in C++ using async.io, this is very performant, so you can monitor your whole /16 subnet or whatever your university or something owns with a single commodity hardware machine. So this, of course, unused IP space you're going to put into your honeypot. Yeah, it's released under GPL. It's like out there for 2 years now, and version 0.2.1 is going to be released soon with some improvements. And main parts of the software are written by Paul Becher and Markus Kötter, and you can just download it for free on the internet. So this is the actual structure of this program. We have these vulnerability modules here that all feed the payload of the exploits to the shellcode manager, which glues these modules with the shellcode analyzation modules. I'm going to explain all of these modules later on. So there's signature-based and also emulation-based shellcode analysis. We, of course, may have to emulate a shell because a lot of the malware uses the bind shell or connect back shell exploits just posted on milworm.com or something. So we have to emulate a Windows shell for these to propagate because they actually exploit a host and then connect to the bind shell used in the exploit and then issue commands, and that's the way to propagate, so they have no real propagation shellcode. And after analyzing this, we get some kind of URL, which is then fed to the download manager, which is the glue between the shellcode modules and the download modules. And at the end of all this, we have a binary we can put on the local hard disk, automatically submit to some Norman sandbox or whatever, or just submit it to some central place via HTTPS. So vulnerability modules, yeah, how do they work? They real poorly simulate the original vulnerability. And most vulnerabilities just work in the way that, or most exploits work in the way that you send n fixed strings called stages, and then just expect some response, and this goes on for, I don't know, 2 or 3 times, and then you send your final payload with the offset and the actual shellcode. And these poor simulations, which are sufficient to work with current malware, just send random junk for all these stages the exploit expect, dismiss all the intermediate stages the exploit just needs to set up the actual vulnerability trigger. And we just take into account the last stage, which includes the payload. And then we either pass the whole payload to the shellcode analyzation modules or just a fixed substring in these modules, because there's the shellcode, and that's what we're interested in. So here's one code excerpt. So as you can see, this really all repli is just a ½ kilobyte. We're just filling it up with random junk and sending this to the malware. And as they're using these public exploits, this isn't a problem, so we don't need more accurate emulation. So this is really simple. But we do need to sometimes adjust some fixed string somewhere so it detects the right target, like to distinguish whether this is a Windows XP or Windows 2000 host or something like that. But usually it's just as simple as sending random junk, some fixed size junk. And then if we are lucky, we actually get the payload from the malware. And then we can analyze the payload for the shellcode. And there's 2 modules. The first one is shellcode signature, which works like the common antivirus software today. It got patterns for the usually occurring shellcodes, and then in these patterns, these are PCRE patterns. It has certain parameters like which host to connect to a back, or which ports to bind the shell to, or for the simple decoder shellcode parts, there's just a XOR queue or whatever. And since patterns are separated into at once the decoder patterns and also the payload patterns, it is really simple using some, like, I guess it's like 40 different shellcode patterns, and with these you can analyze all shellcode that are out there in malware today for propagation. So that's sufficient. Yeah, and then there's a shell emulation, because as I've said, most malware today uses just some stock bind shell exploit, which then this shell emulation just opens the port on the given bind shell port, and the malware then issues some Windows bash, yeah, I don't know, the batch commands, like echo open blah blah into some file, and then executes the stock Windows FTP command line utility on this file, and this shell emulation all interprets these commands and then builds us a nice URL to fetch the malware from these commands. The other shellcode emulation module is based on libemu, which is also a development by the mwcollect.org project. It's a generic x86 emulator which can detect and analyze shellcodes. It's written in C, also by Marcus and Paul. You can download it for free too. It's all GPL. And yeah, as you can see, we also can plot fancy graph with this library, so it's a bit more than just analyzing and detecting shellcodes. And this is, for example, from the LinkBot. So what this actually looks like, this is the control flow graph of the LinkBot shellcode. And as you can see here, we have some XOR decoder. We then have the usual locating of the kernel library, and by hash lookup, like today's Windows shellcodes work, we resolve some library functions, and then first open the socket here, and then this here is the whole downloading, and then here we have some execution of these functions, where this is again actually only a stub to locate a function, which is then called by several sub-functions in the shellcode. And at the end, I guess it's here, we actually have downloaded the malware, and then again call in here to finally execute some of these functions. Yeah, it's pretty small because the shellcode is rather big, to finally execute the downloaded binary on the infected host. So with this approach, we are able to generically detect arbitrary zero-day shellcodes, so to speak, because it's just a full-blown CPU emulator, and any shellcode that runs on the attacked CPU will also be detected by this one, and we know what it does generically. And this is a new development because, you know, in the past, if there was a new shellcode, some users sent us a new shellcode, we had to analyze it manually in some debugger or disassembler, write a new pattern, and this took time, and this just works immediately because it's generic. And then after we build our nice URL from the shellcode, we're just going to download it because they usually use either HTTP or FTP. Some other malware variants use TFTP or even RCP. I didn't know Windows had RCP until I saw some malware using it. And sometimes there are also kind of proprietary commands for transferring the malware. Because, for example, Agobot introduced csend and creceive, which are rather simple because they just send the length of the binary and then the binary itself, and that's it. Or linkbind and linkconnectback, which are really, really nasty because these shellcodes actually generate a per session secret. So for each attack, they generate a new secret. And the secret is actually not just put into the shellcode, but there's code generating the secret put into the shellcode. And this then has to be transmitted on we want to download the malware binary connection. And if the secret is not right, the bot just terminates the connection, and otherwise it works. So this was actually a measurement against this kind of honeypots, low interaction honeypots. But as we could write patterns for this too, we could easily circumvent this. But it required some time of research to see why does it generate this junk in memory, and why does it sometimes terminate connections and whatever, till we figured out, okay, this is kind of a per session secret we have to transmit. Yeah, and also for HTTP and FTP, we first used libcurl, which didn't work out all the time because we had to write RFC and compliant implementations of these two protocols, because the Windows implementations of these protocols were also RFC and compliant. So if you use the FTP stock, FTP command line client, it allows you to do things the normal FTP RFC doesn't allow you to do. And the bots actually were just developed using these command line tools from Windows, and so I guess the bot authors never read any RFCs. So we had to write some broken implementations that are as broken as the Windows implementation, so they would actually work with the malware. So we again had to re-implement these protocols, which was a tedious work, but we had to do it. And that's about it. So as I've said before, there's some alliance, the MW Collect alliance, and this is you can get a picture of what is going on in the world using Nepenthes centers from this. So as you can see, even though client exploits are today said to be the way to go, this is from this week, a picture. So there's still malware spreading using the traditional exploits Nepenthes can catch all over in the world. So red balloons are attacking hosts, and green balloons are sensors. You can see there's malware everywhere, basically. That was a bit about Nepenthes. So let's have a look at some other kind of malware collection tools. PHoneyC is a low interaction client honeypot, because nowadays most of you probably know MPEG or IcePack. There are client-side exploit toolkits, and yeah, it's a big trend because there are way few vulnerabilities like